All right, so what are we talking about?
I actually have a question.
Mhm.
I'm gonna do tonight.
Okay,
Right, so all my math is good, so I was having trouble when I was thinking the LC splice, matching the graph, I don't know if it's a way.
can I look at it really quickly? The voltage. I can just put on and I'll go down.
Instead of, if I can't see the right hand side of the graph, whatever, so you'll turn your equals and move it in.
Yeah,
So. Let's be able to look fast.
Zero micro, 140 micro on the right hand side, going from negative 5.4 to positive 1.2. So there's definitely some issue there. Can I change the color of the letter because I can't read what that mathematical expression says? Really quick. That's homework number one. What problem is that?
No, homework number 8.
So in your simulation, if we look here at this graph or at this schematic diagram, turn around please.
Oh.
Schematic diagram says the switch is opening at t is equal to 0. You have the switch closed during your simulation, which is wrong.
So give me, put it in notes, but it's
For t is 0 plus and greater. Meaning the switch is changing. So literally take the scissors tool. Yep. Yeah. Click on the graph. Rerun your simulation. So your initial condition, okay, so there's another problem there. You have your initial condition of your capacitor carrying the zero matter. So that dot IC should be L in the red. IL should be 5 amps because that's what it got. So let's just run through. Right, and you have there. You have an initial condition on a capacitor current, which means nothing because the capacitor current can do whatever the hell it wants. Your only initial condition should become capacitor voltage and inductor current. So one of your initial conditions is wildly wrong. Change it to the inductor current. So instead of dot, yeah, I'll change it from IC to IL. Or sorry, L1. What it is. And it said, yeah, 5. That's what the balance is. Now press OK. Rerun the simulation.
Thank you. Yeah, I remember that's
That might be your maybe rounding here, but for the most part, they're overlapping together. Yes, okay.
What I thought was, since the problem was asking, the problem was asking for the VT. So I thought we needed to put the initial conditions.
The only initial conditions that matter are the capacitor voltage and the inductor current.
Even the average, doesn't matter what that's.
Exactly right. It doesn't matter what it's asking for. Those are the two initial conditions.
Thank you.
All right, what else are we talking about?
Homework 8, number 4, part 8.
Okay. So homework 8, number 4, part 8. So I'm going to write down problem 4. Assuming that the answers to parts A through D are already correct. So here's our circuit. which is opening at t is equal to 0. I was hoping that somebody would ask about this problem, just because based on the questions that I've gotten from you guys, I feel like I might not have been as clear as is necessary. So we'll sort all that out here, right here, about how this stuff works. So in part E, let me finish defining things here. Here's V of t, IC, and IL. In part E of this problem, we are asked to effectively determine the mathematical model that governs the current IA as a function of time here, okay? So in all of the examples that I worked previously, we were always solving for capacitor voltage, capacitor current, inductor voltage, inductor current, and this is something different. So it's going to require a little bit of thought on our behalf to figure out what's going on, okay? So effectively, what we need to do is figure out how this quantity IA relates to the capacitor current, the inductor current, or the voltage, which is the voltage drop over both the capacitor and the inductor. And so there are a couple of different ways that we can think about this, okay? So we're worried about the point in time during the transient condition after this switch has opened up. So one thing that I can see right off the bat is by applying Kirchhoff's current law, we know that IA of t plus IC of t plus IL of t must be equal to 0, which means that IA of t would be negative IC minus IL. So if we could solve for IC and we can solve for IL, we just take those two things, add them together, and then hit it with a negative sign, and that'll give us IA, right? And every problem that we worked at to this point has been for solving for quantities like IC and IL and all that kind of stuff. So that's one way to do this, but it isn't actually the most efficient way. Okay, so this other way is going to be slightly less intuitively obvious, but if we think about things, they'll be all right. So from the perspective of my energy storage elements, what does this 7 ohm in series with this 3IA source in series with this 2 ohm resistor look like? And I'm not worried about the 9-volt source because during the transient condition, this switch is opened, so this has been disconnected and it's not influencing the behavior at all. So what do these 3 elements in series look like? Nope. But you're getting to the point, it's going to look like a resistor. It has to because this is a parallel RLC circuit, right? We can use the test source method to find the equivalent resistance seen by these 2 energy storage elements, which actually going to come out to be 6 ohms if you did it correctly. So it sounds like you might not have done it correctly, but anyway.
I try to spend like 30 minutes on a problem, so I gotta think about that.
Yeah. So let's prove that really quickly here, okay? So this was one way. It's the way we're not going to do it because it's actually going to be more work doing it this way. So in order to do part D, you would have had to do this anyway. So during the transient condition, our 9-volt source needs to look like it's, and we're finding the Thevenin resistance, so we need to be looking at a dead network. So our 9-volt source has been turned off. Our switch is open because we're during the transient condition. Here's our 2 ohm resistor. Our 3 IA of T voltage source. Here's IA of T. Here's our 7 ohm resistor. $25 millifarad capacitor. .444 Henry inductance. Because we're finding the equivalent resistance with respect to these energy storage elements, we take the energy storage elements out of the circuit. So I'm going to replace them with effectively open circuits. And now I'm going to apply the test source method in order to figure out what this equivalent resistance is. So, should I use a test current source or a test voltage source? Doesn't matter, but one of them is going to make our life a little bit easier than the other. Current. Exactly right. So if we use a test current source, we are effectively saying what IA is, and so we don't have to do any work for that, right? So I'm going to choose to use a test current source of 1 amp. And I'm going to find this voltage V test. And then the ratio of V test divided by 1 amp is my equivalent resistance seen by my energy storage elements. Okay. So I'm going to knock this out in one step using Kirchhoff's voltage law around this path. So I would have negative V test, which is what I'm trying to solve for, plus 7 ohms times 1 amp minus 3 IA, where IA is just 1 amp, plus 2 ohms times 1 amp is equal to 0, which means V test is 7 minus 3 plus 2. So 4 plus 2 is 6 ohms times 1 amp or 6 volts. Therefore, my equivalent resistance is 6 volts over 1 amp is 6 ohms. That's circuit 1 stuff, by the way. Right? So, circling back around, I can treat this whole thing as a 6 ohm resistor without losing literally any information whatsoever, because that's the point of electrically equivalent circuits. We just found out that these 3 things in series is electrically equivalent to a 6 ohm resistor. So treat it as if there were a 6 ohm resistor between this node and this node, or just 6 ohms in parallel with this capacitor and this inductor. IA is then just the current that's flowing through the 6 ohm resistor, which could be easily found by just taking the voltage and dividing it by 6 ohms. So we only need to solve for one piece of information in order to calculate that quantity IA of T, kV.
Does it matter which side you put the resistor on of the voltage source?
There's not going to be a dependent voltage source left. It's just going to be a resistor between this node and this node. No dependent source at all, because we found that the dependent source contributes effectively -3 ohms of resistance to this path based on our analysis here. So if we can find, let me write a line here. using REQ, we can say then that IA of t is just V of t divided by the equivalent resistance, and we don't need to do any other work. So I'll leave it to you guys as to which path we choose to solve for IA. Do we want to use the KCL method, or do we want to use this? Yeah, this is easier. We don't have to, but it's easier, so we might as well. All right, so this is another thing that I think I have been, it seems like you guys are unclear on, okay? So we're just going to use the results from parts A, B, C, and D as if they were correct, because they are. And you were asking about part E specifically, okay? So in part D, we were told, or effectively we found that this circuit is overdamped, okay? Because we chose this particular method to find IA of t, what we're really going to wind up solving for is V of t, and then use that to find IA, okay? So since we're solving for voltage, let's make our lives a little bit easier and consider this voltage to be a capacitor voltage, okay? We could just as easily assume it to be an inductor voltage, and we'll wind up getting the same results, and I can prove that if you want me to here in a moment, okay? But let's say that V of t is going to be where we get our first equation from. And because we have an overdamped response, we are going to have A1 e to the S1t plus A2 e to the S2t plus V at infinity, right? This is our equation for an overdamped response. At t is equal to 0 plus, this simplifies to A1 plus A2 plus V at infinity. Using the values, let me put them underneath here. So V at 0 plus was 0 volts. V at infinity was 0 volts. And so from this, we have the relationship A1 plus A2 is 0 volts. And this is our first equation. Our second equation needs to be a derivative that is related to our first equation, right? So because we are choosing to look at this thing as if we're finding capacitor voltage, then our second equation is going to be capacitor current, okay? So our capacitor current, IC of t, is C dV by dt, or C times S1 A1 e to the S1t plus S2 A2 e to the S2t. At t is equal to 0 plus, this reduces to C S1 A1 plus C S2 A2. So let's throw some numbers in this thing really quickly. So IC at 0 plus was found to be 0.643 amps. C is, let me just write this out here, 25 millifarads. S1 is negative alpha plus the square root of alpha squared minus omega naught squared. Grab a calculator here. I guess I'll use this one because I must have left my TI in my office. All right, so let's see. Alpha was 3.333 neppers per second. So negative 10/3 plus the square root of 10/3 squared minus 3 squared negative 1.880. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. So that is negative 10/3 minus the square root of 10/3 squared minus 3 squared, or negative 4.786. And both of these should have units of per second because they are a frequency. And just plugging stuff in here, we could see, let's see, so 0.025, that's 25 milli, times negative 1.880 is negative 0.047 A1. 0.025 times negative 4.786 minus 0.1196. So let's call that 120. A2 is equal to 0.643 amps. That's equation 2. Solving these two equations will give us A1 and A2. So menu, equation solvers, simultaneous equations, two unknowns. So my coefficient for A1 in my first equation is 1. My coefficient for A2 in my first equation is 1. My constant term is 0. My coefficient for A1 in my second equation is negative 0.047. My coefficient for A2 in my second equation is negative 0.120. And my constant term is 0.643. Solving this system, I get A1 to be 8.808 and some change volts, and A2 is negative 8.808 and some change volts. So from here, we can then say that V of t is just 8.808 e to the negative 1.880 t minus 8.808 e to the negative 4.786 t volts. And IA of t is just V of t over 6 ohms. So 8.808 over 6 is 1.468 e to the negative 1.880 t minus 1.468 e to the minus 4.786 t amps. Looks like I'm off by about 7 milliamps, which is just rounding error because I do my solutions using MathCAD and using the exact numbers. Yes.
So when you use capacitor equation, you would only use the capacitor equation if it's easier than using the inductor equation?
So let's use the inductor equation. Okay. So we're still trying to find this voltage V, but now let's say that that voltage is the inductor voltage. Okay. So our first equation would then have to be for our inductor current. So our first equation is always going to be either the capacitor voltage or the inductor current. And our second equation is always going to be the derivative-based relationship using whatever we chose for our first equation. So since this is an overdamped circuit, we know that our inductor current will be of the form A1e to the S1t plus A2e to the S2t plus IL at infinity at t is equal to 0 plus. This reduces to A1 plus A2 plus IL at infinity. IL at 0 plus was negative 0.643 amps. IL at infinity was 0 amps. And so from this, our first equation is going to be A1 plus A2 is equal to negative 0.643 amperes. Our second equation is going to be our inductor voltage. So VL of T will be of the form, let's see, L di L by dt, or L times S1 A1 e to the S1t plus S2 A2 e to the, S2t at 0 plus. This is going to look like L times S1 times A1 plus L times S2 times A2. We know that VL at 0 plus was 0. We know that L is 4.444 henries. We already found S1 and S2 previously, so we're just going to use those things. So 4.444 henries times S1 of negative 1.880 gives me negative 8.355. .444 henries times negative 4.786, which is just S2, gives me negative 21.269 A2, and this will be equal to 0. So here's our first equation, here's our second equation. So now let's solve for this new A1 and A2. So system solver, 2 equation, 2 unknowns. So coefficient for A1 is 1, coefficient for A2 is 1, constant term is negative 0.643. Coefficient for A1 in my second equation is negative 8.355. Coefficient for A2 in my second equation is negative 21.269. Constant term is 0. Solving, I get negative 1.059 amps, and A2 is positive 0.416 amps. Now, we can say that VL of T is L S1 A1 e to the S1t plus L S2 A2 e to the S2t. And we know what L is, we know what S1 and S2 are, we know what A1 and A2 are. So 4.444 henries times S1 of negative 1.880 per second times our new A1 of negative 1.059 gives me 8.848. $4.444 times S2, which was negative 4.786 times A2, which was positive 0.416, gives me negative 8.848 e to the negative 4.786 T volts, which should be so 40 millivolts off again, probably just rounding error and all that kind of jazz. But we should see that we're going to get the same result either way. I chose to do it as a capacitor voltage because I know that once I find A1 and A2 for that capacitor thing, I get the voltage directly. I don't have to do any extra work. So I chose to solve it as a capacitor voltage just so that I didn't have to do any math to calculate the coefficients because I was going to be given them by solving that system of equations. Does that make sense? Either way is going to get you the right answer.
So this one you use voltage in current to the inductor. For the first example, you use current and voltage to the capacitor.
Yes, absolutely right. So it's always going to be either the voltage or either the capacitor relationships or the inductor relationships. It's how you're going to set up your system. Your first equation should be either the capacitor voltage or the inductor current. And then the second equation needs to be the derivative-based relationship, which for a capacitor is the current and for an inductor is the voltage. Either way you do it, you're going to get the same answer. Did that clarify things at all? Okay, good. So what do we want to look at now, Michael?
So part A of the same problem, how do you set the nodal analysis when the switch is closed?
All right, so first thing, I'm not 100% sure that we need nodal, but let's find out. So at t is equal to 0 minus, our circuit is at DC steady state, which means we are going to replace our inductance with a short circuit and our capacitance with an open circuit. So this open circuit right here represents what our capacitor was at DC steady state. This short circuit right here represents what our inductor is doing at DC steady state. And because we are told that our switch has closed for a long time before opening, our switch is replaced by a short circuit. So we are trying to find the following quantities. So here's IL at 0 minus, here's IC at 0 minus, and this is V at 0 minus. So a couple of things right from the jump is that V at 0 minus has to be 0 volts because it's the voltage drop across this short circuit, and the voltage drop across a short circuit is always 0, right? So because our capacitor is directly in parallel with an inductor and the inductor looks like a short, the voltage drop is always going to be 0. IC is very obviously 0 amps because it's the current flowing through an open circuit, which by definition is 0 amps. So the only other piece of information that we need is IL, and I would argue that we probably want to use mesh because we're trying to solve for a current, so why solve for a voltage and then do one extra step? Okay. So using mesh analysis here, call that I1 and I2, we would have -9 volts plus 2 ohms times I1 minus I2 is equal to 0. KVL around mesh 2, we are going to have 2 ohms times I2 minus I1 plus 3 IA plus 7 ohms times I2 is equal to 0. And we can see that IA is I1 minus I2. And so we just solve this system, and then whatever we get for I2, that is the same thing as IL at 0 minus that we're looking for. So I'll leave it to you to actually solve that system of equations because that's what calculators are for.
Yeah, I did exactly that, but I did not get the right answer. It's because I plugged it in one calculator.
It has to have been because those are the correct equations. So do it better. All right. What else? Yes, Kate.
Homework 9,
Mhm.
problem 3.
Okay. All right. So homework 9, problem E, part 3. Great. So same thing we did for homework 8, problem 4. We're just going to assume that the answers for parts A through D were correct and move along from there. Okay. So here is our big ugly circuit. All right, so in this one, we're asked to determine an expression for IR of P, which is the current flowing down through the 8 ohm resistor. And so the most challenging part of this problem is trying to figure out how this resistor current IR relates to our inductor current, voltage, capacitor current, and voltage, right? So to me, the easiest way to do this is to think of the resistor current as just the voltage drop across the 8 ohm resistor divided by 8 ohms, right? So I'm going to do this in a different color because this is kind of an incidental thing that we're going to have to find. So this is the voltage drop across the resistor. So if I can figure out what that voltage drop is, then I can divide it by 8 ohms to find that resistor current. How can I relate this resistor voltage drop to these quantities? Kirchhoff's voltage law around this loop, right? So VR is VL plus 2 ohms times I of t plus VC. So if I can find VL, VC, and I, that's all the pieces of information I need, and then I just add them together using this equation to find VR, and then I take whatever I got for VR and divide it by 8 to find the current that I'm looking for. The reason why I'm going this route is because otherwise, so like KCL at this bottom node right here, right, we can say that IR is flowing in, I of T is flowing in, but it's not remotely obvious what the current flowing down through this branch is. It seems like it's going to be even more work than doing this stuff over here, which is why I'm not going that particular route. Okay. So do I actually need to go through the steps to solve for VL and VC and I, or now that you've effectively figured it out, are we good to go? Okay. We can do the work if you want to, but that's the method that I would use to solve for that particular thing. Yes.
Was the question asking for just IR?
Yep. That's it.
On the earlier part, it said like part A and the setup of it.
Okay.
Maybe I'm just have to go with my nodal analysis.
Yeah, so let's take a crack at the earlier part then. So this is how to do part E without doing it for you. So let's take a look at part A. All right, so I want to be lazy, so I'm just going to copy this circuit diagram. All right, so for t less than 0 minus, let me write that down so I remember what I'm doing. Our switch is open, so I'm just going to replace my switch with that open circuit. My inductance is going to look like a short circuit. And my capacitor is going to look like an open circuit. So this will be VC at 0 minus, VL at 0 minus, I at 0 minus, and we're not even going to bother worrying about IR until we get to the very end. Okay. All right, so let's look at some things really quickly here. Hopefully it is obvious that I of 0 minus is 0 amps because it's the current flowing through an open circuit. VL is the voltage drop across an inductor at 0 minus, so that's always going to be 0 volts. So the only thing that we need to find is VC. Can't we just use voltage division? So there's no voltage drop across this 2 ohm resistor, which means VC is the voltage drop across this 8 ohm resistor right here. The only voltage source that's actually connected is the 18 volt source. So I think VC should be 18 times 8 over these three added together. No nodal, no mesh, just good old school voltage division because it should work. So VC at 0 minus, if I'm thinking about this correctly, which I believe I am, but we all know I make mistakes, should be 18 volts times 8 ohms over 10 plus 6 plus 8. So where did my calculator go? 18 times 8 divided by 10 plus 6 plus 8. So if you were going to suffer through nodal analysis here,
So when you did, if you were to do nodal analysis, right, it would be, what are the terms, it would be.
So let's say that this one is A, B, C, D. And then I'm gonna leave it at that many unknowns and choose my bottom as ground. And so we know that BC would be equal to whatever VD is. Right? So, just as a quick aside thing here. So we can see right from the jump that VA is 18 volts. KCL at node B is going to give us VB minus 18 volts divided by 10 ohms plus VB minus VD over 6 ohms is equal to 0. So that's this current plus this current, because we know that no current's flowing up, so we don't need to include that path. KCL at D, we're going to get VD minus VB over 6 ohms plus VD over 8 ohms is equal to 0. Solve this system, and we should find that VD is 6 volts like we got earlier.
So when you're doing the nodal at CB, you don't even consider that 12 volt source.
So we could come up with another equation. We could say that VB minus or 12 volts is equal to VB minus VC. And realistically, so I guess you caught me in a slight mistake that literally makes no difference whatsoever. So let me explain what I mean by that. This is a supernode that doesn't contain ground, right? This equation is the KCL equation for that supernode, where effectively we just have plus 0 because the current that's flowing out of C is 0 because it's an open circuit there. So technically speaking, you are correct. We should include it, but in practice, in this particular case, it changes nothing if we ignore it because it's not connected on both sides. So it's not really doing anything. We know that no current's flowing through it. So it can't be really supplying any power to anything. So yeah.
I think I just assumed VB is 12 volt because the source is right there.
Nope, it can't be because it would only be true if we put ground right here, and that's going to make all of our other relationships different. What else are we looking at? Yes. Part E of problem 1 on homework 8. Okay. So we are assuming that the results of A through D are all correct. Okay. I'm going to move that 1.6 over to the other side so that I have a nice convenient place to put V. So in this particular problem, we are asked specifically to find V of t and IC. So we're going to treat both of these as if they were capacitor quantities because IC is very obviously a capacitor quantity. And that voltage V of T is the voltage drop across the capacitor. So we're only going to have to set up one system of equations in order to do this. Okay. So our circuit is critically damped according to part D. So we know that our first equation has to be capacitor voltage or inductor current. And since we're dealing with capacitor related quantities, we're going to go with capacitor voltage here, right? So V of T will be of the form A1 T e to the negative alpha T plus A2 e to the negative alpha T plus V at infinity. Okay. Literally just from the table for a critically damped circuit. V at 0 plus is going to reduce to A2 plus V at infinity, because when we evaluate this guy at 0, A1 times 0 times this other thing is just going to look like 0. Look at the table. We have a critically damped circuit, so we have to use the critically damped response equations. Yep. All right. So do I need to go further? Okay. Our second equation would obviously be the inductor current relationship, which same way we've done it every other time. So, all right, what's next? Yes, sir.
This is more of a general question,
Mhm.
but why exactly do capacitors, when you're looking at time equal infinity, be as focused?
So at t is equal to infinity, we have reached a point in time where our transient condition is over. Effectively, we've taken so long that all of the variations have died out. And so we're at DC steady state again. And at DC steady state, which means we're looking at a DC circuit, a capacitor looks like an open circuit and an inductor looks like a short circuit. So it's critical that we consider T infinity as a long time after the transient condition has died out so that we're back at DC steady state.
What about the capacitor makes it here as?
Okay, so we know that IC of T is equal to C times the derivative of the capacitor voltage with respect to time, right? That is our relationship. So let's say that the voltage isn't changing. What's the derivative of a constant voltage? So C times 0 is 0. So if the current is 0, it's an open circuit. Just as a heads up, if our current isn't changing, then this derivative term goes to 0, which is why an inductor looks like a short circuit, because the voltage drop is fixed to be 0 volts. What's next? Great. Yes. Mm-hmm.
My God.
So you figured out the current through the resistor, but not the current through the capacitor? So it has to be a very simple calculation error. And the reason why I'm saying that, so for problem 2, let me pull it up here on, I'm too lazy to draw. Let's go to my Dropbox. So at least the way that I intended you to do it, this folder will open. You said homework 8, right? Problem 2. Okay. So how I intended you to work this is if you find this voltage, which is the capacitor voltage, and divide it by 5 ohms, you get IR. So if you got IR right, you very obviously calculated the coefficients A1 and A2 for the capacitor voltage correctly. Because this is an overdamped circuit, that means that the coefficients for the capacitor current, let's see. So IC should be C S1 A1 e to the S1t plus C S2 A2 e to the S2t, where if you've gotten everything else right, you know what C is, you calculated S1 correctly, you calculated A1 correctly, you calculated S2 correctly, you calculated A2 correctly. It has to be just a simple calculation error.
I, thought if the, it would be voltage or capacitor. To get A1 and A2.
Mm-hmm. Yep. That would be the easiest way to do it. What did you do?
Did the current through the resistor in my first equation, and then the voltage, the inductor value.
Okay, so the current through the resistor, I don't know how you got anything out of that at all, because for a resistor, you don't have a derivative-based relationship to use, right? So when we're setting up our system of equations, it's always a current and voltage across and through an energy storage element, okay? Because we need that derivative-based relationship so that we have two initial conditions to use. So,
Oh, I did it through the conductor.
okay, so you found,
Same, like, I had the same, current through it, so I broke, but I used it.
okay, so you said the inductor current. So if you found the inductor current, I'm still not entirely sure. Oh, okay, okay. So one thing, okay. Not trying to put words in your mouth or whatever, but so if you found the inductor current and you knew the inductor voltage, then you could do Kirchhoff's voltage law around this loop to find the voltage drop across the resistor, divide that voltage by 5 ohms to get this, and then Kirchhoff's current law at this node. So if you have IL flowing in and IR flowing out and IC flowing out, IC should just be IL minus IR. So that's a way that you could get it based on the information that you already have without having to redo everything. Not the way that I would think you would do it, but nothing wrong with it by any stretch of the imagination. KCL and KVL have to always be true. Yes.
So for this problem, determining the expression for IR,
Mhm.
would you use the capacitor equation because the voltage across the capacitor is the same as voltage across the resistor?
That is what I would do because I'm lazy and I want to do it with the least work possible. Yes.
And that would give you an equation of A and S plus A e to the S. Would that be the final equation?
So this is an overdamped circuit, so your voltage would be A1 e to the ST plus A2 e to the S2t. Divide that by 5 ohms and that's your resistor current. Yeah. Ohm's law is Ohm's law. Why does it need to be more difficult than that? I agree. Yes, Isaiah.
So for this one, you look at the
So this is a parallel RLC circuit. So it may not intuitively be obvious here. So effectively, we need to look at a dead network to figure out whether it's a series RLC circuit or a parallel RLC circuit. So the 5 ohm resistor is definitely in parallel with the 25 millifarad capacitor. With this voltage source turned off during the transient condition, this 3 Henry inductor is in parallel with the other guys. So that's why it's a parallel RLC circuit. Yep. So if we, let me see if we got one with a current source anywhere here. Yeah. So like this guy right here, we have both a current source over here and a voltage source in, right? So during the transient condition, looking at a dead network, this 10-volt source will be off. This switch will be closed. So we would have 3 ohms in parallel with 6 ohms, which is just going to look like a single equivalent resistance. In parallel with half a Henry inductor, in parallel with the 150 millifarad capacitor, and then our current source is going to look like an open circuit. So we effectively are seeing what it looks like with all of our sources turned off during the transient condition to know whether it's a series RLC circuit or a parallel RLC circuit. To find your equivalent resistance, yes.
Okay.
So to find REQ, you're finding the equivalent resistance seen by your energy storage element. So they need to go. And because you're finding an equivalent resistance, you need to be looking at a dead network, which means all of your independent sources have to be turned off. You're just finding the Thevenin equivalent resistance as seen by your energy storage elements.
Never gonna be like something that's going to take off. Like,
I don't follow your question.
so like if you were to look the terminals left from the inductor, you get one equivalent.
So the inductor and the capacitor are in parallel. So it doesn't matter, you're going to see the same resistance either way. So effectively put your, if you have a parallel RLC circuit, draw it such that your inductance and your capacitor are literally right next to each other so that it's just one set of terminals you're looking through. Same thing if they're in series, put them to where they're directly in series and just take out both so that it leaves behind a single set of terminals.
So you're never gonna, there's never gonna be one like like.
No. We will get to those weird things on Monday when we start talking about generic RLC circuits to where we're never going to find the equivalent resistance anymore. We're going to use different methods to calculate alpha and omega. That will work for series and parallel RLC circuits, but the series and parallel is a simplified version. This is way easier than what we are going to be doing on next Monday and Wednesday. Yes.
A circuit always has an equivalent resistance.
A practical circuit will always have an equivalent resistance. So the reason why I'm hedging there is if we had an ideal capacitor, it does not have an equivalent resistance. An ideal inductance does not, well, I guess technically its equivalent resistance is 0, and the equivalent resistance of a capacitor would be infinitely large. But any real circuit is always going to have a resistance because it's made of wires and things that have resistance. So, yeah. Yes.
Both have to be on the analysis of RLC circuit.
That's it. Yeah. So the in-class portion of exam 2, we have all the material covered. It's literally just series and parallel RLC circuits. And then the take-home portion of exam 2 is going to be dealing with a general RLC circuit because they are such a pain in the ass that it will take you longer than a class period to do one of them. Yeah. Once you get through all the algebra, it's easy. It's literally just the algebra of setting up your differential equation is a pain in the butt.
So, we're not currently paying for the portion, correct?
I don't know, whatever the syllabus says seems legit to me. 14th is next Friday, right? That sounds about right. Today's the 5th. 14th.
Yep.
Yeah. 12th, maybe? Yeah, 14th is a Sunday, 15th is Martin Luther King Day, so it's either the 12th or the 17th. My money's on the 12th. It's on the syllabus. Let's let Walker figure out when the test is real quick and then we'll get checked. Yes, sir. Well, okay. All right. What's your question?
I'm just, making my graph again to match, and it's for some reason it's inverted.
Class period.
That's number 2.
Mouse over the resistor R1. So you see how that arrow is pointing up? Yep, so you actually need to have right click where you have R1, like in your graph. Literally like where you have R1. Now, move over and put a negative sign in front. So notice how the scale on the right-hand side and the scale on the left-hand side are not the same. So mouse over the scale on the right-hand side, put the maximum value to be 2.4. And the minimum value to be 0. Yep. Out the top. Doesn't matter below or above. Now the number up, so you did it right.
Did that have to do because the resistor positive and negative terminals were backwards?
I thought this was happening.
Yeah, it's just the way, however many times you rotated it, it chose to say that the positive polarity terminal was on
So
positive.
this just happens to just start negative sign.
Yep. Okay. That's what the arrow on your current probe tells you what direction the current is flowing in, and so it's obviously different than the way that I defined it. So a negative line.
Okay, thank you.
All right, what's next? Or I guess we have 3 minutes, so can I leave? All right. You guys have a good weekend. All that jazz.